of your talk. Okay, I think we're ready. So whenever you want, Aljosa, please go ahead. The floor is yours.
Yes, thank you very much for your kind introduction. So, hi everyone. Before I continue, just a quick question. Can you all see my slides, my screen?
Yes, perfectly.
Okay, fantastic.
At least the first one.
Okay, yeah, I think it's gonna work. Yeah, so thank you very much for inviting me today. I'm very happy to be here and to talk about our recent research work, and I'm going to talk today about perception. So let me first quickly motivate kind of research problems that we are working on in our lab. So what we want to do is to enable mobile robots, such as those that you can see here on the top, to navigate and move around our world. And to do that, of course, robots need to be able to detect and track objects. And in addition to localizing objects and understanding how their trajectories evolve, we also need to understand the semantic meaning of background structures. For example, we need to understand where the road is, or in more general, where the drivable surface area is, so that we can plan our motion trajectory ahead. Now, these are kind of topics that I'm going to discuss in the first part of my talk, where I'm going to talk about holistic dynamic visual scene understanding. So here I'm going to cover topics such as object detection, segmentation, tracking, and semantic segmentation, and we are going to try to tackle them jointly in a holistic unified framework. So then in the second part of the talk, I will move on to the difficult problem of tracking arbitrary objects. And to explain a bit more what I mean by that, so what you can see here in the output of this system that you can see here on my slides, we trained first object detectors for car and pedestrian classes. So we had labeled data for cars and pedestrians, we trained object detectors, and we could track these objects reliably over time. But the problem is that in case we see objects for which we didn't have our training data in the set, such as a child stroller over here, we are essentially blind to such an object. And this can, of course, lead to disastrous consequences. And it has actually led to disastrous consequences before, when a Tesla car that was on autopilot didn't recognize the fire truck as a valid object and just crashed straight into this fire truck. So this is something that we definitely want to avoid. So you might be thinking now that, okay, we can just go outside, record more training data, label more training data, and then train also detectors for strollers and fire trucks. But I would actually argue that this is not quite as simple because of this long-tailed and unbounded object class distribution. So this distribution essentially tells us that we will observe few object classes very frequently, such as cars and pedestrians, for example, but the vast majority will be observed very rarely. And the most problematic is that this distribution is unbounded. And the implication of that is that during the deployment phase, we will always see objects that didn't end up in our training set, right? So this will always happen. And even for most of objects that will appear in our training set, we might observe very few instances of them because of this long-tailed object class distribution. And because of that, I would argue that we will never be really able to obtain enough training data to train a reliable object detector for every possible object class. Okay, so as I said, I'm going to cover two topics today. And first, I'm going to talk about holistic dynamic scene understanding. So here I'm going to talk about tracking every pixel of the video or every 3D point that comes from a stream of either sensory data. And then in the second part, I'm going to move on object tracking the open world, in which a set of object classes that you want to track will be unbounded. So first, I'm going to talk about tracking every point and pixel. So here I would first like to talk about our very recent work that we presented at CVPR a few weeks ago, and this is This was done in collaboration with Cyril Stachny's group in the University of Bonn and our group at Technical University of Munich. So here I'm going to talk about LiDAR-based scene understanding or LiDAR-based perception. And just quickly talking about kind of perception problem we were looking at as a community when it comes to LiDAR perception. So for example, in case of semantic segmentation, we want to classify each point, right? You want to assign semantic meaning to each point, but we're not aware of instances in this case. In case we do both instance segmentation and semantic segmentation, we are talking about panoptic segmentation. But here, the focus is still on interpreting single LiDAR scans. A bit orthogonal to that is the task of 3D multi-object tracking. And here, the way people usually do this is that to first train 3D object detectors based on LiDAR inputs, and then associate these detections over time to get such object tracks. And in this work, we actually proposed 4D panoptic segmentation that unifies all these perception tasks. So for this task, we actually need to assign semantic meaning to every 3D point in the sequence and a unique object instance ID in space and time. So in terms of tracking, the most popular paradigm used up to now is called tracking by detection. So I already briefly mentioned this, and here the idea is that we have a few sensor inputs. So let's say 3 different consecutive LiDAR point clouds, and what we would do is we would first train object detector, then apply object detector independently to each LiDAR scan. We would obtain the 3D object detections independently in each LiDAR scan, and then by some means we would try to associate these detections over time, very commonly using Kalman filter-based framework or something like that. And once we do that, we obtain our tracking results. So this is a standard pipeline, and here in this work, we really decided to go for something rather different. And we were inspired strongly by the perceptual grouping theory that says that points that are nearby in space look similar and have a good continuation likely belong to the same object. And you kind of extended this idea to spatial temporal domain and formed here tracking as grouping of 4D spatial temporal volumes. I will explain in more detail what I mean by that very soon, but first let me just note that we first introduced this idea of tracking as clustering in the context of video segmentation in the paper that we published at ECCB last year. And I will also briefly mention this work in the next slides. First, I would just like to outline the overall idea behind this approach. So here the main question was, can we learn 3D point embeddings for a point cloud sequence, such as this sequence that you can see here on the left, such that points that correspond to the same object are mapped nearby in the embedding space. So points that correspond to this green vehicle here that will be observed in the different point clouds, you want to map all these points nearby together in the embedding space. And I want to do that for each object. And one of the main insights here is that we can actually model object instances in such spatial temporal volumes as Gaussians. And if you do that, then we can do the following. Imagine that we have a object instance, let's index it with J, and we want to evaluate probability that some point in the short spatial temporal volume belongs to this instance J. So let's index this point with I. And to evaluate this probability of this point belonging to this instance, what we need is embedding vector for the query point from this spatial temporal volume. And we will also need embedding of our object instance J, embedding vector for this instance J. I will soon explain how we get to this exactly. Let me just finish this by also noting that we need the variance vector for our object instance J. And this will be exactly the parameters that we will need to learn here. So to explain how exactly we do that, let me first go one step back and explain these ideas in the context of video object tracking. And the sole reason why I want to do that is that it's a bit easier for me to talk here about images because in this case, our spatial temporal volumes will be three-dimensional. So we have two spatial dimension and one temporal dimension. So it's just bit simpler to explain ideas and looking at this kind of data. And this is exactly what we did in this ECCV paper that I mentioned last year. So here, the big idea behind this would be that we have a short video clip that you can see here on the left. We would stack images of this short video clip together, and we would pass this clip through our encoder-decoder based network architecture. And on the top of the decoder, we would have 3 network heads. So one network head provides us embedding vectors for every point in the volume. Second network head will provide us a variance vector for every point in the volume. And the third embedding head is called cluster center heat map, and you can really interpret this head as a point-based spatiotemporal object detector. So what this head will give us is, it will give us it will be kind of heat map, and it will tell us what is the most likely object center of object instance in the video clip. So it's kind of point-based object detector. And once we trained our network and we have this information available, then we can do inference as follows. So here in this video clip, we have 2 object instances. So one will be the rider, and the second one will be the horse. And then what we do is we will look at our cluster center heat map that is visualized here, and we will take argmax, right? So if we take argmax, then we obtain then we'll obtain center of a certain object instance in the spatiotemporal volume. And let's say that this point here is in the middle of the clip, in the center of the rider here. So we take argmax and we read out the coordinate of that value over here, and then we perform a lookup into our embedding map and a variance map, right? So this is how we obtain a representative embedding for our instance and representative variance vector for our instance. And once we have this information available, then we can evaluate probability of each point in a volume of belonging to this particular object instance, right? So we'll just go through all volume, assign points to this instance. So this will be points for which probability of this point belonging to this instance will be higher than 0.5, and then we will take these points out of the volume, right? And by doing that, we'll essentially get we will essentially segment this object in this whole video clip. And then we just iterate. So once we took these pixels out of the volume, we will take the next argmax that will probably center this horse over there, and we will just repeat this procedure. So this is the big idea behind the overall idea behind this approach. So now going back to LiDAR data. In case of LiDAR data, what we'll do here is we will slide a fixed temporal window over sequence of LiDAR sensor data. And from each such window, we will sample a set of points. And when we sample a set of points, we'll obtain a 40-point cloud volume. So this will be kind of point cloud volume where we just warp all these point clouds together in a single point cloud. And then this 40 volume will be input to our encoder-decoder based network. Again, just in this case, you will have a backbone that can operate with point clouds. And just as before, we will add on top of the decoder 3 network heads. So objectness head, which is again acts as a point-based 3D object detector, and point variance and point embeddings head that will help us to assign points to their respective object instances. And in addition to these 3 heads that I already presented in the context of video instance segmentation, we will also add a semantic head that will classify each point into a fixed set of predefined object classes. So then at inference time, everything works in the same way as before. And then as we are sliding this window over the sequence, we can obtain final results in online manner by processing overlapping volumes and associating these obtained temporal segments based on a simple overlap criterion. And here our experiments indeed do show that by enlarging the size of the temporal window, we will significantly improve segmentation and tracking performance. So now I want to outline some results that we get here with this method. So first, we evaluated this method for the task of single scan panoptic segmentation. So benchmark for that already existed before. And what we evaluate here is a special case of our method where the temporal window size will be 1. So here we are talking about segmenting a single scan. And here you can see that even in this setting, our unified single network already quite significantly outperforms existing method in terms of panoptic quality. So this is this PQ metric here. It's standard metric for evaluating the quality of panoptic segmentation, and also mean intersection over unit. So this is the metric that is widely used for evaluating semantic segmentation quality. Here, I would also like to mention that several baselines here actually use separate networks for semantic segmentation and object instance detection, and then fuse the results. And we here just trained one single network for this task. Now, in the next slide, I'll present results for the 4D LiDAR panoptic segmentation. And before I go there, let me just quickly explain that the baseline for our method will be tracking by detection approach. So in tracking by detection approach, what we will do is we will take all these methods that I listed here. So those methods operate on a single scan. We will then again process every scan independently and by some means associate these segments over time. So this will be the tracking by detection baseline. We have results here in this table for our new LiDAR, 4D LiDAR panoptic segmentation benchmark. And when I'm going to talk about results, I'm going to interpret results in terms of the new metric that we also introduced in this paper, and it's called LiDAR segmentation tracking quality, LSTQ. I won't go into details of this metric. Let me just explain on a very high level that it decomposes into 2 terms. First term is called association term, and it signals us how well we can associate points in this 4D space-time volume. So essentially, it will tell us how well we can segment and track objects. Then the second term will be so-called classification term, and this one tells us how well we can, in terms of semantics, classify points, and this will be just standard mean intersection over union. Okay, so here we have first we have true tracking by detection baseline. So the first one is based on the Kalman filter-based 3D multi-object tracker. And this is the result that we get with our single scan variants when we use this tracking by detection framework. And the second tracking by detection baseline is based on pre-trained LiDAR SynFlow method. So we use pre-trained network that estimates LiDAR SynFlow, and we would use this SynFlow method to propagate segments from one scan to another. And then we compare this to our method that directly processes several scans, so spatiotemporal volumes, then determines overlaps between those. And what is the most striking here is that the association quality dramatically increases, as you can see here. So we obtain much better results in terms of association as expected, of course. So in terms of classification or semantic segmentation, the results don't really improve much, but this is to be expected because we expect to gain the most when processing multiple scans together in terms of segmentation and tracking. And here the conclusion is that our method that processes several scans in parallel actually performs significantly better in terms of association. And overall, our single stage and unified network quite significantly outperforms this tracking by detection baselines, and it actually does not need any external methods or networks for temporal association. So everything is handled by the network. And here I have a short video of this system. So here on the left, you can see semantic segmentation results, and on the right, you can see instance segmentation and tracking results. On the left, the color encodes the semantic class, and on the right, the color encodes the object identity, object ID. Okay, so this was the first part on holistic video and LiDAR scene understanding. And now I will move to the second topic on to the tracking in the open world. And here I'm super excited to talk about our very recent work, opening up open world tracking. And this is a product of a great collaboration between our research group at Technical University of Munich, group of Bastian Leibe at RWTH Aachen University, and group of Deva Ramanan at Carnegie Mellon University. So first, I want to give you some motivation why we are interested in this problem. So one of the big questions is whether we can learn to recognize new classes by just looking at raw streams of sensory data that actually robots do observe. And really think we can, but we need to figure out how to decompose videos such as those that you can see here into the basic units, so objects. And this is why this is one of the reasons why we need the tracking component here. And in this video, I was actually showing, let me play this again. I was actually showing our past work on the topic of generic object tracking. And what we kind of did here is we developed these trackers and then we applied them to hours of footage that were recorded in Oxford. So this is Oxford robot car data set. And once we extracted such video object proposals, we performed clustering. So we clustered these object tracks, and then we were experimenting with training new detectors automatically based on these clusters. So all patches from tracks that end up in the cluster will now be used as a training data. And it turned out empirically that we can actually train object detectors in such a fashion. And you can see two examples here. So for example, a detector for this sign bollard that you can see only in Oxford or in UK emerged here, and also object detector for cones, for example. So obviously these are rather proof of concept results or early results, but the main point here is that I think that the tracking is really important when it comes to such automated object detector training. So of course, one thing that we wanted to understand here is how well we can actually do tracking in the open world, right? So how well we can actually track unknown objects. And with this work, we actually aim to study that. Mm-hmm. So to put now this work into perspective, in relation with previous tracking tasks and data sets, if you look at mod challenge, we are focused on tracking most common object classes, right, such as cars and pedestrians. Now, recent automotive data sets expand number of object classes a bit. And actually, recently, our collaborators at Carnegie Mellon published this awesome TAO dataset that actually enables us to study multi-object tracking in this long tail scenario. But here, the focus was still on the closed world regime. And actually, with this work, we really take tracking even further, so right into the open world. So here we base our open world tracking benchmark on the TAO dataset, of course. And what we did here was we declared 80 object classes that are part of the COCO dataset vocabulary as known object classes. So we will only train our models on the COCO using these 80 object classes that we call known object classes. And those will be the only classes that will be seen during the training phase. So these classes are visualized here on the top. The remaining classes that you can see here at the bottom, we call them unknown classes, and those will not be seen during the training phase. So 300 of these unknown classes are present in the validation set, and then we have additional 143 classes that will only appear in the test set. So those classes we call unknown unknowns. And we think that they are quite a reasonable proxy for the wide range of objects that could appear in the real world. Okay, so this is the data set in that we use to evaluate in the splits. But the next important question is, how do we quantify the performance, right? So what we did here was we built on or recently proposed higher order tracking accuracy metric. So this is a new tracking metric that we introduced, that we published in this IJCV paper last year, and we adapted it here for open world evaluation. And our open world tracking accuracy metric that we introduced in this paper decomposes into two terms. So the first term here, we call it detection recall, measures recall. And here we decided for recall-based evaluation because in the open world setting, we can't really define a notion of false positive, right? So if we wanted to penalize false positives, then we would need to label every possible object that could ever appear. And this is pretty much impossible. So the second term will evaluate the tracking aspect of this task and will tell us how well we can associate instances into object tracks. And this term will be evaluated with respect to every true positive, and it will take form of intersection over union over sets of true positive associations, false positive associations, and false negative associations. So these terms were introduced in this HOTA paper that we published last year. And let me just give you a very brief intuition of what these sets quantify. So because this is evaluated with respect to each true positive, let's focus here on the true positive of interest that is here denoted with this red angle. So here we have two ground truth trajectories. So one is the dark blue one and one is the light blue one. And then we have two track predictions. One is denoted with black circles and second with gray circles. So whenever tracks, so ground truth trajectory and predicted trajectory with respect to this true positive will mutually agree, we will have true positive association. So this is the green region over here. Whenever we will have a tracking error where another predicted trajectory jumps onto this ground truth trajectory, so the dark blue, we will have an error that we call false negative association. And the other type of error occurs when this black trajectory jumps on another ground truth trajectory. So these are the types of errors that this term will quantify. So now I want to just highlight some key results that we got with this method. And first, let me explain that input to our tracker here will be a mask RCNN that will be trained in a category agnostic setting. So only to distinguish between objects versus non-objects and generate the mask for every object. And here the main focus of this work was actually to rigorously study how to associate object proposals that we get from such mask RCNN over time. So here I should probably also explain that the main difference between standard mask RCNN and the category agnostic variant of mask RCNN we use over here is that we won't really threshold detection. So we won't only take most confident object detections, but we will take several object detections per frame. So I explain more about this in a minute. So by studying how to associate these proposals over time, we also obtained our open world tracking baseline, and I won't really have time to discuss all design decisions behind this baseline, but I will outline a few key results here. So the first thing that we did was we studied how well our category agnostic variant of mask RCNN performs on unknown classes that were not seen during the training, and this is what I'm showing in this plot here on the left. And let me just also quickly mention that we are not discussing tracking results. So this is just a single level evaluation at this stage. And here I'm showing detection recall for unknown objects versus a number of proposals for different scoring methods. And here one conclusion is that commonly used two-stage detection object detectors such as MASCAR CNN already generalize quite well to unknown classes. As you can see here, it suggests that they inherently already have like any object detector built in. And we can, as you can see here, also quite reliably rank them, which is very important because we cannot fit 1,000 proposals to our tracker, right? Okay, so on the right, I'm showing track recall at varying percentage of detections that were correctly recalled. So to explain this a bit more, 50% detected means that at least half of the track must be correctly localized. And here you can see that there's really quite a big difference between the tracking of known and unknown objects. Because, for example, here you can see that only 25% of unknown objects are recalled in every frame compared to 70% for the known object classes. So in this regime, in open world regime, data association will actually be much more challenging. And this is why we also made this thorough analysis on how to perform association. And I'll just final results on this work. So here I am actually showing tracking results. So for both known and unknown classes. So here I'm showing results for open world tracking accuracy metric that I mentioned earlier. And here we have detection and recall, and then association recall and association precision. And here first we are looking at the Tau validation set, and we are comparing our methods to two state-of-the-art methods on the closed world Tau benchmark. And these two are used here for reference only because those were trained also for unknown object classes. So these are not open world trackers. And what is interesting is that our open world tracking baseline actually performs better for known object classes compared to this closed world baseline. And we believe that this is due to our very careful design and analysis on how to associate objects. Of course, it falls behind for unknown objects, both in terms of recall and association accuracy, of course. But this is not surprising because both Oracle methods have been trained to both detect and track these unknown objects, and open world tracking baseline was not. And this also highlights this gap that we still need to bridge. So the second table here shows results of our baseline on the test set. And here I need to mention that so far we evaluated and analyzed our baseline on the Tau open world validation set, and this is like the set where we have chosen, evaluated and chosen our best design decisions. And here we really want to evaluate our tracker in a true open world setting. And in this setting, we have, of course, known objects, unknown objects, and even unknown unknowns that are unique to this Tau test set. Open world test set. And here the main conclusion is that open world tracking baseline performs similar between the validation and the test sets for known and unknown objects. But even more important is that our method actually performs similarly on the set of unknown unknowns that are unique to the test set as it does on unknown classes that are also present in validation. And the final tables that I'm going to show today so here what we did was that we evaluated our open world baseline in the closed set setting on the closed set benchmark. So they with unsupervised video object segmentation data set and Kitty mods. And what is interesting here is that even though our method was not tuned for any of those data sets, our method is actually very competitive on both data sets. So here it only falls behind UNOVAS that was specifically tuned, very specifically tuned to this data set. And here on Kitty mods, when we use the same inputs as all other methods, so public detections, it's on par with state of the art. So performs best for car tracking and is slightly behind point track for pedestrian tracking. Okay, so now just to some visual results. Here on the top, you can see a few results of some visual results for tracking of known objects. Here at the bottom, unknown objects, so those that were not seen during the training. And even more interesting than that, we also just notice that there are these other objects that are being tracked and are not even part of the Tau vocabulary. So these are essentially objects that our trackers discovered. and this would be this would be those that could be considered that are like valid objects, but could be considered as false positives because these objects weren't even labeled in this data set. And now we reached the end of my today's talk. So I think that here the main takeaways is that tracking can be posed as clustering. So this is like a new bottom-up approach to a variety of object tracking and segmentation related tasks. And also this approach is actually applicable to methods for holistic and dynamic visual scene understanding. So either based on video input or LiDAR sequences. And I think that the next grand challenge that we need to tackle, and I think that we can spend the whole next decade pretty much on this topic, is perception in the open world. So detection, tracking, and segmentation in the open world. Thank you very much for your attention. And if you have any questions, I would gladly answer them.
Thanks a lot, Aljosa, for this interesting talk about definitely next challenges in open world perception, right? So let's see if we have maybe we have time for a quick question, because I think we're running out of time. The main conference has a keynote soon, if I'm not wrong, or is it starting? I don't know with what, but let's see. Anybody has any question for Aljosa? You can raise your hand. I actually had one curiosity. Maybe I can go first. So in the clustering part, when you talk about your 4D strategy that you compare with different tracking strategies that use your approach combined to Kalman filter, or your approach combined to the flow estimation, and then your multi how did you call it, your multi-scan approach, yeah. Right? So I'm just trying to get the intuition there. So it was a big gap, right? When you go to your multi-scan approach, then the key difference is when you go to multi-scan that you apply your 4D clustering in different windows and then just combine. That is better than running any other type of tracking, let's say, any like Kalman filter based tracking, or is that the main, like the key there? Or I don't know if I'm missing some detail, like what's the key difference between your single window and single scan, multi-scan, or if I understood, single window or multi-window, right?
Yeah, that's a great question. So the difference is that in a multi-scan approach, we feed several scans to the network, and network will implicitly resolve associations, right? So it will provide us segmentation and tracking directly within the temporal window. So if there are occlusions, the network will directly resolve those, right? Then, yeah.
No, sorry. I was thinking. So then you train the models with multi-scan also. It's not the same. I think I was understanding it wrong. So it's not the same model that you apply differently. You learn it differently from the beginning. You learn with multi-scan.
Yeah. So the only difference will be that the temporal window will be of length 1 in the case where we use Kalman filter, right? So in this case, we only get segmentation results on per scan level, and then we need some method to associate those. So this is like tracking by detection, where we detect objects in individual images or scans and associate them. So it's the same method. It's just that window size parameter will be different.
Okay, then the real 4D comes when you use your multi-scan. Otherwise, there is not really. Okay.
Yeah. Otherwise, it will be 3D plus temporal association.
Okay. I think I got it now. Thank you for the clarification. So I don't know if we have any additional quick question. Otherwise, we can maybe make the break here. We have now a long break because of the main conference. So we will come back in 3 hours from now after the main conference sessions finish. So I think, if I'm not wrong, is that right, Eduardo? In 3 hours
Yes.
from now, right?
When I stop.